Okay, so just as a reminder, we looked at these two examples of the drop and the throw, and we use our intuition to answer some questions. So we're going to use some numbers now in order to make some calculations given the scenario to show that our intuitions were correct. So the first thing I want to do is review the basic equations that we have right now. Okay, so we learned that velocity is equal to the change in displacement over time. Okay, and this is actually, we had the example of driving across the country from Asheville to Seattle. Okay, so as you drive, if we were able to drive straight, that direct line from Asheville to Seattle, in our car we might have to stop at stoplights, we might go 100 miles per hour, then we go 50 miles per hour. So actually, if we take the entire change in displacement divided by the time that it takes, we're actually getting the v average, or the average velocity of the time that we, or the average velocity that we were traveling. Okay, now the other equation that we have is the equation for acceleration. So acceleration is equal to the change in velocity over time, okay, which we also wrote as a being equal to v final minus v initial over time. Okay, now, I can also, algebraically manipulate this. You might also see it as, AT equals VF minus V0, or V sub naught, which means V initial. And we can algebraically rearrange it in any which way, which we'll do in order to solve problems today. So those are the two equations that we have. And again, remember that we're talking about the special case of constant acceleration. So first, we're going to look at a dropping problem, so dropping something off the cliff, right? Okay, so let's just say we're going to completely ignore any sort of horizontal motion, so we're just dealing with verticals, ups and downs. So if I were to stand up on top of a cliff and just release something, okay, not throw it up or throw it down, just let it go, then what is the initial velocity? Okay, so if I just let it go and I just release it, at the very instant when I let it out of my hand, the velocity initial is actually 0 meters per second. Okay, so that's important to note. Now, let's say we let the ball drop all the way down to the bottom of the cliff, and let's just say at the bottom of the cliff it's going 100 meters per second. Well, because velocity is a vector, we need to indicate direction. So we would say that our v final, and we're just making these numbers up, is actually negative 100 meters per second, because we want to indicate that it's down towards the ground, because it's traveling, it's accelerated down due to gravity, and so the final velocity would be negative. Okay, now I just pointed out a good or just made a good point about acceleration. So we do know acceleration in this case as well. So acceleration, which we write with the little letter g if we're talking about acceleration due to gravity, is equal to negative 10 meters per second squared. Okay, so this is just all some information building up to a problem. So let's look at solving how tall the cliff is given this information. So our question is going to be the height of the cliff. Okay, so the height of the cliff is the variable that's going to be represented in our math is actually going to be d, or our displacement, or a change in displacement, right? So let's look back up here in these equations. We have this, okay, which v average is equal to the change in d, and I'm just going to write d over t, okay? And so if I were to solve that for d, I would say, well, v average times t equals d. All right? Now, what is v average? I have my velocity at the beginning and I have my velocity at the end. Okay? And what is great is because I have a constant acceleration, I can take the velocity at the end and the velocity at the beginning and divide it by 2. So if I take v final, just like I do any other sort of average, plus v initial divided by 2, that actually gives me my average velocity. Now, it is very, very important to note that this is only when acceleration is constant. We can't ever use this anytime that acceleration is not constant. Okay, so if I were just to plug and chug in here, remember my V final is negative 100, my V initial is 0. Okay, so if I take 100 plus 0 divided by 2, I actually get my average velocity is negative 50 meters per second. All right, now my original question was what is the height of the cliff? So I just found V average, so that's one thing I need. But the other thing that I need is time. So I need to figure out if there's some way that I can solve for time given that I have these three knowns. Okay? So if I look up here, I have this equation where it has V final minus V initial all over T equals A. So that's a variable that involves, or equation that involves the variable T, and I have the other three variables. So let's just plug in to that, and I will solve for the amount of time that it takes to drop. Okay, let's go to the next slide. So I have acceleration equals V final minus V initial all over T. I want to solve for T, so I'll multiply by T on both sides. AT equals V final minus V initial, and then divide by A. This cancels. So we get T equals V final minus V initial all over A. Okay, and then I'm just going to plug in my numbers. I know negative 100 minus 0 all over my negative 10 is going to give me a time of 10 seconds. All right, so remember I had V average times T equals D. And I use this equation to find T, and I use my last equation to find V average. So my V average was negative 50 meters per second. My time is 10 seconds. So I get my seconds cancels, negative 500 meters. So that's 500 meters down that the ball fell, okay? Which is actually, if my question was the height of the cliff, so I would say, it's 500 meters is how tall the cliff is, okay? So this is a sort of roundabout way, and I'm going to derive an equation where, given the variables, remember that I was asked D, okay, and I was given V initial, VF, and A, okay? I'm going to derive an equation where I can solve for D given that I do not have time, just given those other variables, okay? So I'm just going to go through the steps that we did before, but now we're just going to do it algebraically, okay? So remember, I have that D equals V average times T, okay? And V average is equal to V final plus V initial all over 2, okay? So I could plug this in for V average and get that my D is actually equivalent to, write it up here, D is equal to V final plus V initial all over 2 multiplied by T. Okay, so now we want to eliminate the variable T. So again, remember that I had T equals V final minus V initial all over A, which we got algebraically up here. Okay, and so we're going to plug this in for T. So now I have that D equals V final plus V initial over 2, all times V final minus V initial all over 2A. Oops, sorry, all over A, sorry. Okay, so now we just want to multiply this out. We got to do a little FOIL action here. V final minus V final minus negative V initial, and I'll just go ahead and write out what that is. We get that D is equal to V final squared minus V initial squared, all divided by 2A. Let me rewrite that on the next page so that we have more, you can see that better. Okay, so D is equal to V final squared minus V initial squared over 2A. And how we see this in our reference tables, we'll just algebraically rearrange. We want to solve, it's written solved for V final, okay? So V final squared is equal to V initial squared plus 2AC. This should be memorized. Okay, that is one of our constant acceleration equations. Okay, so now let's use this equation to prove one of our original predictions. So one of our original predictions was that the ball that we throw up in the air is going to be going faster when it hits the ground than when we just drop it. Okay, so let's say we have that same cliff, right? And now I throw the ball up at 30 meters per second to begin with. Okay, let's put this up here. So I throw the ball up at 30 meters per second. My cliff is still 500 meters. And because the ball starts and ends at the same place, even if I just throw it up in the air, that is going to be my D displacement. Okay? So I have, what am I asked? I'm asked V final. Okay, how fast is it going when it hits the ground? And I'm given things that I know are V initial is equal to 30 meters per second, that my D is equal to negative 500 meters down, and that my acceleration is negative 10 meters per second squared because it's gravity. Okay. Now I will just plug and chug. Vf squared equals 30 squared plus 2 times a negative 10 times a negative 500. Okay, so this right here is actually 900. This gives you 10,000. So if we add those together, we get 10,900. And we know the square root of 10,000 is 100. So the square root of this, and just to avoid using a calculator, I already have the answer for you. It's 104 meters per second. So remember, our original prediction was that the ball that is thrown up in the air takes longer to hit the ground, or is going faster when it hits the ground than the ball that was dropped. This was going 100 meters per second. This was going 104 meters per second. Okay, so we just derived an equation that proves our original prediction.